I'm recording this just so you know. So the game plan was to just do some problems that are similar to your homework. Unless you have any specific things you want to talk about, that's just what I was going to do. Okay. So let me get, I was confused on the homework, so that would be great. Okay. All right, everyone, I got you. Very confused. Awesome. All right. You know what I mean when I say awesome. Okay. Let's see. Let's do this one. So I'm going to show you something. Give me a second. Not ready. Not ready. Okay. Go here. And then hit share. No, actually, I changed my mind on what problem I wanted to do. Go here and do all this. And then, so one of the, where is this problem? Okay. So one of the problems you may or may not be confused on is this one, when I finally put it up there. Share. I know it's blank, it's okay. Don't worry about it. Okay, can you see that? Maybe?
I can see it.
Okay. So we'll talk about this problem because I'm thinking this is one of the ones you're confused about. Maybe. Okay, take a picture. Get your, I wish there was a way I could still see what chat somewhere. Okay, it's not gonna show me it. That's fine. All right. Okay. Everyone got their picture? I'm assuming you do. Come back to it later. All right, cool. Okay. All right. So I'll write it down again just in case. Okay, so we're looking for the pH and we have 0.91 molar C2H5NH3I. Okay, I'm looking for the pH of this. We're looking for pH. Oh, equals, maybe equals question mark. Okay, and then the problem, is an interesting part. They give us a KB for C2H5NH2, right? Okay. Alrighty. Okay. Big thing you probably notice is that this is not that, right? That's not that. Those two are different. But maybe what you also notice is that, okay, I write my C2. I'm going to break this up into two ions, right? So this is generally I minus, right? That becomes I minus. That was an ion. And then this guy would be H5NH3 plus. Does everyone see that? You can just put in yes in the chat if you want. Yes, cool. Okay, yes, why did you do that? So good question. So this is aqueous, right? This is an aqueous solution. So I guess I kind of cheated here. Let's do this. So I have my C2H5NH3I. This is aqueous. And when I put it in water, so I'm putting in my H2O, it really exists as C2H5NH3 plus I minus. These are aqueous as well. All right, so this is what they really show up as in the water. Oh, can you see this? Oh gosh. Sorry, give me a second. All right, okay. This is what they really show up as in the water. Right, so that's I'm looking at. We're just focusing on this guy right here. The I minus we don't really care about. For reasons that we'll now point out right now. Okay, what do you notice about this and that?
They're not the same?
They're not the same. What else?
It loses a hydrogen.
Lost a hydrogen, right? So what does that mean? Conjugate, I think there's a conjugate base pair, right? These are conjugate pairs. Yeah, I'll do it. Conjugate pairs, right? Okay. All right, so that's going to help, right? We know that these are conjugate pairs. And this one is what? Like with respect to acid or base?
The acid.
Acid, good. Okay. So this is an acid. So we need a Ka. Oh, I'll write that bigger. Ka. Does anyone remember how to get Ka from that Kb?
Use the KW formula.
Yep. So I use my Ka, Kb equals Kw, right? And Kw, put it up here. Kw is 1.0 times 10 to the negative 14. Okay, so we can get Ka. Ka is the Kw, which is that, so 1.0 times 10 to the negative 14 over my Kb. I didn't even write it. Okay, good for me. 5.6 times 10 to the negative 4. So much math already. I have my calculator around here somewhere. I got 1.79 times, I guess 1.8. Oops. 1.8 times 10 to the negative 11. Everyone with me so far?
Yes.
Yes. Good. Yes. Alrighty. Okay, so now you have a Ka. You have an amount, again, we're ignoring this part. You have an amount of a weak acid sitting in water, and I'm looking for pH. So what do we do now?
Do we write that equation now with the acid plus water?
Yes. So I write my acid with water equation. So my C2H5 C2H5NH3 plus H2O goes to C2H5NH2 plus H3O plus. Right, and then your states. I just know this one's liquid. Right, okay. Right, then we do our ice table, right? Or is, let me ask, is everyone okay? Everyone can figure out how to get this? Is everyone comfortable doing that?
So you were given it as a product. That's what you're given.
So I was given it as a product. So in here, I'm representing it as a product because this is this salt disassociating, right? I know disassociate in water first, and then this part is going to react with water and give me my pH thing.
Okay.
Does that make sense?
Mm-hmm.
Okay. Any other questions so far?
Is that 0.91 molar up at the top? Is that just a dummy number?
No. This is important. I'm going to use it in my ice table here.
Okay.
Right. So when I do my ice table, so ICE, good question. Right. I don't care about what's happened to water. My initial amount is actually that. Right. My initial amount of this is that because this is going to completely dissociate. I probably should check my solubility rules, but I'm just assuming it works. So we're just going to run with it. Okay. Right. Everyone comfortable with what I have so far?
Yes.
Are we going to be given the solubility rules, or do we have to memorize them?
We'll give them to you. You do not, I don't think you have to memorize them. You just have to know how to read the chart, the table. Okay. And then it's just a regular thing. So we put 0, 0 because we have none of those in there, right? And then minus x plus x. So I got 0.91 minus x, x, and x. So now I have, what do I have? I have my k, so 1.8 times 10 to the negative 11 equals 0.91 minus x over x squared. Right, everyone? It's getting kind of cluttered. Everyone? Good, makes sense. No questions.
Why do you use the Ka instead of the Kb?
So here in this equation, this is the acid one, right? This is for the acid. Right?
Gotcha.
Okay, yeah. If we had used, if that was in the thing, then we use Kb, right? So make sure when you're, whatever reaction you're doing, just make sure it matches with your K whatever. So this is acid reaction, so it's Ka I need. Okay. I'm just going to assume x is small, right? I have 10 to the negative 11 here. That's 10 to the negative 1. So that's more than 4. So I can, that's a good assumption that I can make. So get rid of this guy, do my math, and I get x is what? Let's see. Take this. 8 times 10 to the negative 11 times 0.91 square root. I got 4.0 times 10 to the negative 6. Can you explain why you got rid of the minus x squared again? I mean minus x. So here, I'm assuming that this is my X is small assumption. So X is small. So basically I'm saying that when I subtract X from 0.91, after rounding for sig figs, I'm gonna get 0.91 again. And the reason I can do that is I look at my Ka and I see that it's 10 to the negative 11. And I go to my initial amount of my acid, and I see that if I wrote that in scientific notation, I would get 10 to the negative 1. Right, because I would just move my decimal place over 1. So 10 to the negative 1. As long as that is greater than 4, the difference between, negative 11, negative 1 is greater than 4, then it's a good bet that you can make your X is small assumption. And then we still have to check it to make sure it's greater. This is less than 5% of that. But that's just a good check to see if the X is small assumption is a good thing to look at.
Okay, thank you.
No problem. All right. Okay, let's check it. Running out of space. That's fine. Let's see. Do it right here. So I'm going to do the 4.0 times 10 to the negative 6 over my 0.91 times 100. And what is that? That is so that's 0.0004%, which is definitely less than 5, so we're good. Right, that just means that this X we can put with it. Okay. All good. Are we all, is everyone okay? Great. Ginny, I'm gonna meet you. Okay. Awesome. All right. All this work, one more step. We need pH, right? So I'm just going to take the negative log of that. So pH equals negative log of 4.0 times 10 to the negative 6. And so my pH is 5.39.
I have a question.
What's up?
So we're given a KB, right?
Given a KB, correct.
So why did we have to find K? Like, could we have just done this whole problem, like, in terms of what we were given being a base?
Well, okay. So let's assume. So the issue with that. So this substance isn't in the bottle, right?
Okay.
You see, and so you can't. So you have to work with what's inside of there. If you did it with KB, assuming that's KB, you're going to get something basic, right? You're going to get a basic,
Mhm.
which is not correct because in there you have an acid, technically. In reality, you have an acid in there. And so if you run through all this with your base, you're going to have an OH minus right there, probably, most likely. And then here you'll do your POH and then get a pH that is basic. You'll probably get that as your POH, and then you'll minus 14 and get a basic pH.
So how do you know, like, from when you read the problem statement, how do you know that you're gonna have to find Ka?
So the big hint for me, and what I usually look for, is notice that what they give you, the KB for what they give you, has one less H than the stuff that's actually in there.
Okay.
So that tells me, oh, these two are conjugate pairs besides that I. You gotta ignore the I. So another thing is identifying that this is a salt, and when it breaks up, it's gonna break up into these two things. And this is what
Okay. Got it. Okay. Okay. Thank you.
no problem. Anything else? Any other questions? No. Okay. All right. Sweet. So I'm gonna erase this. I'll leave it up for a little. Let me get the next problem that I want to do. Which one? SPH. Do you guys are comfortable identifying Lewis and Lewis acids and bases, maybe?
Can you go over them?
No, okay. Yes. Oh, sorry, Eugen. I was just reading the chat. Okay. I'm gonna erase all this. There are I'm putting these all on YouTube, so if like you miss something, you can go watch it there and get it hopefully. Let's see. So we've been mostly dealing with Bronsted. Oh, camera, please. Okay. We've been mostly dealing with Bronsted and Lowry, Bronsted, Lowry, acids, and bases. Bases, okay, that's the same. So the acids did what? Do you guys remember? What do oh, please, okay. What do Bronsted Lowry acids do?
Just donate a proton.
Donate protons. And then bases accept said donated protons, accept protons. Okay, and then Lewis, Dr. Keene talked about it in one of his videos. Does any of you?
They give up and accept electrons.
Yeah, right. They acids give up. Maybe hold on. Let me double check. It all has to do with lone pairs. I always forget which one is which. So yeah, so bases donate lone pairs, and then acids accept said lone pairs. Okay, one example. Okay, I'm gonna erase the Bronsted-Lowry definition because we know that. Where's my eraser? Here it is. So one thing we can look at is NH3 plus, we'll keep it simple. We'll do H plus. We'll just look at H plus goes to NH4 plus. So if I draw out my NH3, you guys remember from your Lewis structures maybe. So it looks like this. And then H plus is just that. Right. And then NH4, we'll draw NH4. H, H, and then H. Okay. So you see my lone pair on my base right here is getting donated to this H right here, right? It's this NH3 is sharing its lone pair with H to make NH4. Everyone see that?
With this like acid base system, do you have to have hydrogen, or like can it be any compound?
That is right. I do not have, this good observation. I do not have to have a hydrogen. I could put Cl right here. Let's put Cl. Cl minus. Or do I want? We'll just do Cl, regular Cl. We'll pretend like that works. And then this becomes CH. I don't know what it is really, but we'll just pretend it's Cl3L plus whatever. I don't know. I don't think. Whatever it actually is. I don't care about the charge on this one. And then this becomes Cl, right? And this is just Cl. Cl with 7 dots. Maybe 7 dots. Whatever makes it work. I'm gonna do it 6. Okay. Again, similar thing. My Lewis structures may not be right, but it doesn't matter right now. That's not what we're concerned about. Okay, I have my lone pair being donated to this Cl, and the Cl is accepting them by making this bond. So now this is a Lewis acid, right? This is now a Lewis acid, but it's not a Bronsted-Lowry acid, right? Right, there's no proton for it to give up, so it can't be a Bronsted-Lowry acid. Right, so a big thing that you can notice between Lewis, what Lewis allows you to have is acids without H's on them. So that's the main difference between Lewis acids and Bronsted-Lowry acids, is that Lewis acids have the potential to not have an H bonded to them. That clears it up. Thanks. No problem, everyone. Make sense? Awesome. Cool. Sweet. Okay. Is everyone comfortable just finding pH like we did in the, like if I were just to give you an acid and say, hey, find the pH of this concentration of whatever weak acid, and I gave you the Ka. Is everyone comfortable doing that? Yes. All right. Yes. 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 Awesome. All right. So are there any more chapter 16 questions? I'm about to move to chapter 17. So ask your chapter acid-base questions now before, well, I guess you can ask them later, but I'm giving you an option to ask them now. I'm taking no answer as a no questions. Okay, good. All right. So let's do molar solubility stuff. Let me see, I have some. Okay, let's do, we'll use this question for more than it's supposed to be used. Do my little trick. Also, let me know if you have any, suggestions or things you would like to see that I'm not doing, or something you'll like to see done better, because I am taking all suggestions. Okay, so we're going to look at this question right here. It's one of your suggested problems. I think this N is supposed to be lowercase. I'm assuming it's supposed to be lowercase. Or that's supposed to be magnesium. That's why, magnesium. Okay, take your pictures. Okay, so we're looking for the molar solubility is 4.2 times 10 to the negative 6. Everyone remember that. Okay, let's stop. Okay, so we have, almost forgot, magnesium carbonate, and we know that the molar solubility is 4.2 times 10 to the negative 6. Is that right? Hopefully it is, because I told you to remember it, and I didn't remember it. It is, good. All right, awesome. Do you guys remember what that means? That this is the molar solubility?
Is that S?
S, yes, right, it's S. It's the S. And then we did our equation, right, for KSP is MgCO3, that's a solid probably, goes to my Mg2 plus CO3 2 minus. Right. No, oh, S question mark, okay, never mind. Okay, so we got my ice table, ICE, right, and you ignore this. We have none of those, and then you add S, right? We did S here instead of X, so that's the S inside question. Oh, I drew that so big. Okay. All right, now we know that KSP is equal to these two concentrations times each other. And you get, so that's S squared, right? Right, just I did S times S, so S squared. And so that's going to be my 4.2 times 10 to the negative 6 squared. And so KSP, yeah, okay, is 4.2 times 10 to the negative 6. Oh, I just didn't square it. I just spit back the same thing. Okay, there we go. 1.76 times 10 to the negative 11. Not now, Fox. Okay. Right, nothing too crazy yet. Anyway, makes sense. Yes, okay. All right, so simple problem. I think we did something pretty much close to this in class. So, okay, my question. So let's say I went and I'm gonna add MgCl2 to this solution. Oh yes, is that a 10 to the negative 11? Yes, it is. All right. Okay, so I'm gonna add some random amount, or just some amount of Mg. So this is like part 2. This is part B. Conceptual question we're gonna add on here. So if I add some random amount of MgCl2, I want to know what's going to happen to S. Or what's going to happen to S, essentially.
We will have to determine if MgCl2 is aqueous or not.
Yes. Is it aqueous?
Okay.
Hopefully it is.
If it is, then it'll shift left.
Right. Let's assume it's aqueous. I don't know. I'm pretty sure it is.
Okay, and then S would decrease.
Yes, my S would decrease, so my solubility would go down, right? Right. Does that make sense?
Can you explain that?
So I put in MgCl2 and it's aqueous. I'm gonna erase some of this stuff. Okay, since this is aqueous, when I put it in the water, it's gonna break up. So MgCl2 aqueous. It's gonna go to, it's gonna be a straight arrow. Mg2 plus Cl minus 2. And those are aqueous as well. Right? So by throwing this into my this solution I have of magnesium carbonate, I've added some more Mg2 plus. Right? And if you remember your Chatelier's rules, if you add more products, it's going to shift it in the left to the opposite direction. So by doing that, my S right here is going to go down. This amount right here is going to decrease to bring it back to equilibrium, essentially. Right, less of this is going to dissolve because there's so much in there already.
So it becomes minus S.
It'll still be plus S because you still have a 0 over here, right? You'll have something right here, some number.
So it just changes it from 0 to an actual number.
Yeah, change it from 0 to actual number, and then you'll get plus some actual number. And then that in turn is going to decrease this S. And your solubility is gonna decrease. So by adding more of the product, I get less of a solubility of this. Okay, got it. Good. Any questions on that reasoning?
I have a question. So how do you know, like on the left side, you have MgCl3. And so how do you know when the number that is like I know it's not called a subscript, but that's like what it looks like. How do you know when that becomes a stoichiometric coefficient?
Okay, so this is just your nomenclature practice thing. So you have to know, like go to your periodic table. Let me see if I can find one real fast. Go a quick one. Periodic table. Let me take this off so you don't have to look at all my tabs. I have a lot of tabs on my computer. Share this one. Okay. Hopefully you can see that. So I have to remember, okay, for Mg, this one, it's +2 because it's in the second column, right? It has a charge of +2. So that's where I got, you can't see it. I'm gonna stop sharing this. That's where I got this +2, right? I knew Mg is +2. You can kind of figure out that CO, well, you can't actually. You have to remember that carbonate, which is one of your polyatomics, was a charge of -2. And so since they have the same charge, right, when I cross them out, I would cancel. Up here, I have to remember, okay, Mg has a charge of +2, right? If I remember that Cl is a charge of -1, then I know that, okay, that 2 is significant to the 2. I guess that was a kind of tyrant to not answer your question. But the main question is, I knew that this is a polyatomic, so I knew that the CO3 stayed together. Up here, that's just a regular chlorine atom. And so, oh, I know I have 2 chlorines, so I'm going to break that off. I think that was actually what you're asking me, and I went off on a tirade. Got it. Cool. Does this make sense to anybody? I have another more difficult KSP problem that'll probably help you in the homework. If we have time, can we do one more problem like the first one? Yes, we can. Okay, let me do this last KSP problem first, and then we'll go back. Where's mine? Here it is. Let's do this. Bum, bum. Bum, bum. I'm sorry if my mumbling to myself annoys you. Okay. So I give you the solubility of a compound M2H5NH3I. Give you the molar mass of that, right? I give you solubility in grams per liter, and we want to know the KSP. So similar problem, kind of more complicated. Okay. I'll write it down right now. So M2H3, and molar mass is 288 grams, and then the solubility is 3.6 times 10 to the negative 17 grams per liter. Okay. Again, we're looking for the grams per liter, or not grams per liter, KSP. Okay, this is grams per mole. So is that S? Question for you. No, correct. It's not S. This is grams per liter. Hopefully you saw that. I didn't think it was S. So we need to make it grams or moles per liter, right, for S. And we can do that since we have the molar mass up there. So let's do that real fast. So we have 3.6 times 10 to the negative 17 grams per liter. And then we have 288 grams is 1 mole. Quick fix. We got 3.6 times 10 to the negative 17 over 288, right? Yes. We got 1.25 times 10 to the negative 19 is S. Okay. All right. That's S. Anyway, all right, next. Let's write our KSP equation, right? Reaction. So let's do M2X3 solid equilibrium goes to, okay, now I have to be careful here. So I have 3M, I'm just gonna assume, or 2, 3, no, 2. Yep, almost messed up. That's okay. 2M3 minus. Right. That's aqueous plus 3x2 minus. The charges don't, or 2 plus, or this one's plus, that one's minus. The charges don't really matter. We're not doing anything with them. I'm just putting them up there to make my life more complicated so I can make more mistakes. Okay, 2 minus. That's also aqueous. Again, these charges don't really matter. You don't really need them. These coefficients are important. Those, not so much. Okay, so my ice table. I'm gonna do it for good practice. Do my bars. Don't care about the solid. Okay, I have 0 of that, 0 of this. What do I put here?
Plus 2s.
Plus 2s, correct. And then that plus 3s. Okay. To 3. Plus 3s. Okay, I got my 2s, 3s. So I got that KSP equals. Okay, gotta be careful here. What do I put? So let's write out our concentrations. So M, the 3 plus, and then X2 minus. Is that right?
You need to raise it to the powers of the coefficients.
Right. So don't forget your powers here, since we have a 2 and a 3. Right. So this is squared. This one is cubed. And so that's going to be 2s squared, right? And then 3s cubed. Some people get confused because they think, oh, I used this 2 twice. That can't be right. But it is. It shows up in there twice, right? Once there, and then once in the like coefficient. Okay, then be careful when you're squaring and cubing things. What's that? That's 4s squared, and then 27s cubed. And so KSP, someone also should be double checking my math, just in case, is 108 s to the 5th. Right, and now we just plug in our s that we have up here. So we get KSP is 108 times 1.25 times 10 to the negative 19 to the 5th. I got super small, 3.29 times 10 to the negative 93.
Did you do the 108 times the 1.25 10 to the negative 19 first and then raise it to the 5th?
So this is, the 5th is just for the s part. So it's 108 times 1.25.
Mm-hmm.
The 10 to the 5th power is just for the s. So I did 1.25 times 10 to the negative 19 to the 5th.
Okay.
108.
And then multiply the times 108.
Correct.
Okay.
So yeah, this is here. I can. So it's a step I skipped because I did. I'll put it right here. 1.22925 times 10 to the negative 19 to the 5th. That's what I did. If you can read that, this is a 19. That's okay. It's a 19, negative 19. Questions? No. Awesome. Great. So just the main mistakes people usually make is right here, forgetting that either writing right here instead of 4s squared, they write 2s squared, or maybe just getting concerned that they use the 2 twice and getting rid of one of them. So just watch out for that. Also in the homework, I think for a problem that was kind of like this, he gave you this as the name. He just gave you the name, so just double check your nomenclature and make sure you can do that. Comfortable doing that. Okay. What? Oh, Eugen wanted to do another one like the first one. And the first one, that was the salts, right? No. Oh.
We calculated the pH and then it gave us like KB. We had to find Ka.
Yeah. Okay, good. Ooh, through the book. Let's do. All right, no, go fast. Calculate the pH. Sorry, I'm rewriting one that I want. This is KH. Okay. All right. Sum it up. As a now. Alrighty. Look at this. Here it is. Okay, let's do that. Okay, write down need. So we have 0, 0, 2, and molar NaF, and then Ka Okay. All right. So any thoughts on what we should do first? Dissociate NaF. That's good. Yeah, let's do that. So NaF is aqueous. So it goes to Na plus F minus. These are both aqueous as well. Okay, disassociated both of them. All right, what do you notice?
It gives you the conjugate base for the Ka that we're, or the acid that we're given.
Yes. So I have the conjugate base up here for the acid that I'm giving. So yes. So right, I need the so in here I have the conjugate base. So I need Kb, right? I need the Kb of that. Everyone, that makes sense to everybody. Okay, I'm assuming yes. Can you explain that again? Okay. So when we disassociated it, so notice that this part, we have F minus, which is a conjugate base to this HF, right? If I write out my HF equation, right? So I write HF plus H2O gets me F minus plus H3O plus, right? And you see these are conjugate pairs. Okay. So really, in this solution, what you have is a base, right? This F minus is a base. That's a base. Right. So you want, when you're trying to figure out the pH of this solution, you really have a base reacting with water. Right. So this is what I have. This is the equation you actually have. This is in solution. What's really going on is F minus plus H2O goes to HF plus OH minus. You see, right? And then to do our ice table with this is, right, we need a KB. That's a KB reaction because we have OH minus, so you need KB. Does that help? Yes, okay, good. All right, I'm gonna erase this part right here. All right, now we can calculate our KB. Let's do that. So again, we're using our KW. So KB equals KW over KA, which is 1.0 times 10 to the negative 14 over that, okay, 7.1 times 10 to the negative 4. And so KB is something. Is negative 14 over 7.1 times 10 to the negative 4, 1.4. Yeah, 1.4 times 10 to the negative 11. 1.4 times 10 to the negative 11. Write it over here just for kicks and giggles. 1.4 times 10 to the negative 11. Good. All right, do our ice table. ICE. Okay, don't care about water. What am I going to put for this initial amount right here?
The 0.082.
Correct. Okay, 0.082. And then 0 for those, as we usually do, because there's no mention of those. Okay, so minus x plus x plus x. Get 0.082 x. Now we get KB equals 0.082. I'm going to put what the number actually is, 1.4 times 10 to the negative 11. 0.082 minus x, I forgot my minus here, over x squared Okay, again, 10 to the negative 11. This would be 10 to the negative 2. So I'm going to make my x is small assumption. So I'm assuming x is small, get rid of this one, right? I can only get rid of x's that are added or subtracted to something else, right? Don't get rid of the top x's, or, you know, you can't solve for anything. Okay, so let's do this times 0.082 square root. Oops. I got x is 1.1 times 10 to the negative 36. Again, we got to check and make sure it's less than 5% of that. So 1.1 times 10 to the negative 6 over 0.082 times 100 over 0.082 times 100 is 0.0013%. Definitely less than 5. So we're good. Check mark. This is good. All right, now I'm here. So, okay, do I just take the negative log of that and am I done?
No, because it's OH.
Correct, right? It's POH. To make sure none of you are sleeping. Okay, POH. Right, because I have OH in here. So negative log of my 1 point, or I guess you could do divide by KW if you wanted to, but whatever you want to do. Negative 6. Right. So my POH is negative log, excuse me, is 5.96. And then my pH is 14 minus 5.96. So pH is 8.03. Right, do my little sanity check. Okay, this is basic, right? And we had a base in there, so that's good. That's a base, this is basic. Sanity check complete, and we're done. Okay, it's 9:05 and did kick us out here, so that's good. I wasn't sure what was going to happen. All right. Okay, good. Any other questions? Last minute questions. It is 9:05, so we're technically done. But if you have any questions right now, okay, good, got it. Did everyone sign in on the Excel doc? Yes. Okay. Good. No. Here, let me put the link. Let me get the link for you, Jania. Okay. Go. There's the link. You go there and put your name and your student ID, and then check the box if you're an athlete. But other than that, yeah, we're all good to go. So if you have no more questions, you guys can go ahead and get on out of here. I won't see you guys tomorrow, but I'll be there in spirit in tomorrow's Zoom session. Well, not in spirit, I'll actually be there in tomorrow's Zoom sessions, and I'll have that SI same at 9 tomorrow. We'll probably be doing more chapter 17 stuff. Bye, everyone.